Good morning. In today's lesson, we start proving that triangles are similar. Lesson 7-3. We'll be covering two different academic standards this morning. GT4, given two triangles, use the definition of similarity to decide if they are similar. And GT5, use properties of congruent and similar triangles to solve real-world and mathematical problems. Our objective of the day, students will be able to prove that triangles are similar. You'll also be able to use similar triangles to solve problems. Let's begin with our first postulate today, the angle-angle similarity theorem. Remember that all triangles add up to 180 degrees, and if two angles of one are congruent to two angles of another, then the third angles are automatically congruent. So our postulate today says, if two angles of one triangle are congruent to two angles of another triangle, then the triangles are similar. If A is congruent to P and angle B is congruent to angle Q, then triangle ABC is similar to triangle PQR, the angle-angle similarity. Take a look at these two problems. Are the two triangles similar? How do we know? Well, in problem 1A, we have triangle RST and triangle NOP. Since R is congruent to N and S is congruent to O, the triangles are similar by AA. Triangle TSR is similar to triangle PON. That's our similarity statement. In problem 1B, right now we have one pair of angles that are definitely congruent. The second pair we don't have yet, but we still don't know those third angles. So we'll find the measure of angle H by taking 180 minus 80 plus 40. That means angle H is 60 degrees. Angle F, 180 minus 45 plus 40. So angle F would be 95 degrees. So since no two angles are congruent, the triangles are not similar. We didn't satisfy the AA similarity postulate. Our next postulate, or theorem in this case, is the side-angle-side similarity theorem. Similar to side-angle-side congruence, we have to use two sides in the included angle. In this case, if two sides of one triangle are proportional to the corresponding two sides of another triangle and the respective included angles are congruent, then we can conclude that the triangles are similar. AB to DE is equal to AC to DF, and angle A is congruent to angle D, then the triangles are similar. Our third way to prove that triangles are similar is the SSS similarity theorem. The lengths of the sides of a triangle are proportional to the lengths of the sides of another triangle, then the triangles are similar. Notice that we have to write the extended proportion because we need all three ratios to be the same. Let's look at what these would look like in action. Problem 2A. Are the triangles similar? If so, write a similarity statement. Well, let's test our ratios. PL would match up with KR, which is 5 to 10 or 1 to 2. PD is corresponding to KS, 12 to 24, also 1 to 2. DL is corresponding to SR, which is 13 to 26, also 1 to 2. So since all the sides are in proportion, triangle LDP is similar to triangle RSK by SSS. Take a look at B. We would compare the sides of ST to TR. Notice the ST is 10, TR is 14, because we'd have to add 10 plus 4 to get that. TU compares to TV, so it's 12 to 16.8. Again, to get that 16.8, we simply add the 12 and the 4.8. That gives us the proportion 10 is to 14, as 12 is to 16.8. Using the cross products property, 10 times 16.8 is equal to 14 times 12. Both products are 168, so the sides are in fact proportional. Finally, notice that angle T is congruent to angle T because it's reflexive. They both use the same angle of T. Therefore, triangle UTS is similar to triangle VTR by the side-angle-side similarity theorem. One of the ways that we use similar triangles is to do indirect measurements. And we use an indirect measurement to find lengths that are difficult to measure directly. One method of indirect measurement uses the fact that light reflects off of a mirror at the same angle with which it hits the mirror. So take a look at problem 4. Benjamin places a mirror 40 feet from the base of an oak tree. When he stands at a distance of 5 feet from the mirror, he can see the top of the tree in the reflection. If Benjamin is 5 feet 8 inches tall, what is the height of the oak tree? So here's a visual of what this is going to look like. Again, Benjamin is 5 feet 8 inches tall. You see him down in the left corner. The oak tree is what we don't know. The mirror is 40 feet from the base. When he's 5 feet from that mirror, he can see the top of the tree. So we write a proportion. His height, 5 feet 8 inches. And again, you got to convert these all to the same measurements. So I converted 8 inches into 0.67 feet. So 5.67 is to 5 as x is to 40. Using the cross products property, 5 times x equals 5.67 times 40, or 226.8. We'll then divide by 5, and we discover that x equals 45.36, the height of the oak tree. That concludes Lesson 7-3 on proving triangles similar.